Hello, welcome to today's webinar. We are happy to have you with us for this session, Getting to Zero in Affordable Multifamily Buildings. This webinar series provides ongoing opportunities for knowledge sharing around actionable solutions to drive the highest levels of efficiency in buildings. I am Connie Umphris, Communications Manager here at New Buildings Institute. Before we begin, I have a couple of housekeeping things to tell you about. First, you are muted and we cannot hear you. This helps keep the background noise down so that everyone can better hear the speakers. I want to direct you to the dashboard that you should be able to see on the right-hand side of your screen. If you are having technical difficulties and cannot see the slides or hear our speakers, you can use this question pane in the dashboard to let us know, and we will help you as we go. We will take a few questions at the end of the presentation. Please ask questions in the same question pane. Please take a moment to answer the survey at the end of the webinar. We consider your input in the planning of future sessions. If you are seeking AIA credits, this survey is where you will share your AIA number for credit submission. The session is being recorded. All registrants will receive an email tomorrow with links to the recording and slides for the session. If you need a certificate of attendance for your records, it will also be part of tomorrow's follow-up. A little about NBI. We have been in the energy efficiency space for 25 years, working to protect people and the planet through efficiency solutions. Save the date for the 2021 Getting to Zero Forum in October in New York City. Find out more on our website at gettingtozeroforum.org. Here's today's panel. I would like to introduce our moderator today. Atalia Howe is the Manager of Sustainability Programs at the Community Preservation Corporation. The CPC is a nonprofit affordable housing and community revitalization finance company based in New York City. There, she supports CPC's role as a leader in promoting energy efficiency and high-performance building practices, as well as a strategic partner to both public and private organizations to drive market adoption of sustainable building design. Atalia, over to you.
Thank you, Connie. Assuming everyone can hear me okay. So yes. Welcome everyone. We've got a terrific panel for you today. We'll hear from professionals focused on net zero energy design with a special focus today on the affordable multifamily sector. We'll hear about some new resources from National Renewable Energy Laboratory, providing net zero energy design guidance by building type and climate zone, supported by case studies and energy modeling. And we'll walk through some case studies from different climate zones. So we've got something for everybody. Then finally, we'll wrap up with some Q&A from the audience. So without further ado, I'd like to introduce our esteemed panel. Dr. Paul Torsellini is the Principal Engineer for the Commercial Buildings Research Group and has been at the National Renewable Energy Laboratory, NREL, for 23 years. Prior to this role, he was Group Manager for the Commercial Buildings Research Team. He also spent 3 years as a technical advisor to the U.S. Department of Energy in Washington, D.C. Paul was an instrumental part in creating the process to achieve the zero energy building status for NREL's research support facility. Maya Gantley is a project manager at the Association for Energy Affordability, AEA, a nonprofit dedicated to providing energy efficiency to affordable housing communities. She is a technical analyst for the Low Income Weatherization Program, providing energy savings calculations, scope development, and project management expertise. And Walid Al-Ghamdi is an Associate Director, Smart City and Sustainability at Roshan Real Estate. He is an experienced building professional in the fields of architectural design, energy efficiency, sustainability, and building performance, with a focus on HVAC and lighting systems. He has worked in both the United States and Saudi Arabia in a wide range of work settings, from a large global leader in the architecture, engineering, and construction energy industry to a small specialized niche firm. So before we jump into the presentation, I very briefly want to introduce CPC. CPC is a nonprofit tax-exempt 501c3 affordable housing and community revitalization finance company. CPC was formed in 1974 as a direct response to the issues of property abandonment and blight that New York City was facing at the time. Our mission was and continues to be to bring low-cost capital and fresh thinking to the complex issues facing communities. CPC provides a full suite of products to finance multifamily housing and to create and preserve affordable housing. Today, we are one of the largest community development financial institutions in the country solely dedicated to investing in multifamily housing. To date, we've invested over $11 billion of private and public capital in the Northeast region, which translates to approximately 196,000 units of quality housing in neighborhoods across New York State and beyond. Just very briefly about CPC's sustainability platform. The sustainability platform was created in 2003 to carry out CPC's energy efficiency and decarbonization goals. CPC is a carbon neutral company. We measure our carbon emissions on an annual basis. We have a formalized reduction strategy internally, and then we offset remaining emissions on an annual basis. We've developed a number of tools and resources to educate and inform and engage the multifamily industry, including the CPC Verify tool, which is a software application that calculates potential utility savings and helps owners explore the financing options and cost savings for different multifamily building upgrades. We've developed the underwriting efficiency guide, which hopefully many of you know and have used. It was a guide to provide lenders and public partners and owners with a resource to finance energy and water efficiency measures as part of a first mortgage. We recently launched a new guide, which there's a slide on next, so I'll hold off for that. And we also partner with public and private organizations, mission-oriented organizations, and we continue to explore new financing incentives to promote and encourage energy efficiency and decarbonization. And just lastly, very quickly, I'll make a quick plug. This is a new guide that CPC created. We recently launched this just last month on high performance new construction. The guide is designed for multiple stakeholders within the multifamily ecosystem. It tackles the basics of high performance design and how those design decisions can affect life cycle performance, value, risk, and overall asset health. So we really look at, what is a high performance building? We explore some of the factors that are increasing demand for high performance buildings, such as climate legislation and new requirements from capital sources. And then we kind of do a deep dive into the building life cycle. So looking at how high performance guides decision making and cost decisions, and how it affects operations and maintenance, and appraisal and resale throughout, again, that building life cycle. And finally, we look at some of the non-energy benefits that high performance creates. So you can access that guide here at this website. If you're interested in receiving a hard copy, we're happy to send those to you. You can just reach out to me and we'll send me your address, and happy to send you a hard copy. So with that, I'd like to pass the mic over to Paul, and he will walk us through this presentation.
Okay, thanks. So I want to talk about the Advanced Energy Design Guide for multifamily buildings in this session. And let's see if the slide will advance.
Click on into the window, Paul.
Yep.
Oh.
Did you see it advance on your end?
No.
No.
I'll go ahead and take over.
Try
See
it
if
again.
it works. How about that?
Okay. All right, let's do that. So first, I want to talk about the Advanced Energy Design Guides, but before I start, they are really based on a concept of a zero energy building. And we're using this definitions as a basis of that. It's really about the balance between the consumption of the building and getting the consumption down to the point where renewable energy can supply the remaining needs. Next. And a lot of it has to do with where we draw that boundary. And so these buildings are connected to the grid. So I want to make sure that everybody gets that, it is a transaction between the grid and supplying energy as well as producing energy on site. If there's an excess, it can be exported, and not only can be exported to the grid, but it could be exported to other uses such as electric vehicles. Next. When we start thinking about this, we really think about how much energy is available at the site. And for most people, that renewable energy is coming directly from solar and then through photovoltaics. And so while there are other resources, other renewable resources available, a lot of what we are focused on is the photovoltaics from the production side. And so you can see here a graph of the United States. In some areas of the country get a lot more sun than others. We can actually extend this worldwide. But one of the things that we've done is we take this and we translate that to how much energy can a building consume based on its size and the number of floors. So this analysis was done on a 2-story building with 75% of the roof covered. And you can see someplace like Southern Arizona could use 44,000 BTUs per square foot as a EUI target, whereas moving up into New England, it could be half that amount. Next slide. And what we strive to do is to get that EUI to match what the consumption is of the different buildings. So kind of moving into the Advanced Energy Design Guides, which really is kind of implementing that thinking. These guides have been around for many years. They are published by ASHRAE, but they're put together as a cooperative effort between ASHRAE, AIA, U.S. Green Building Council, and the Illuminating Engineering Society. Funding comes from the Department of Energy, and the national labs have provided the technical support and a lot of the modeling to show the feasibility and the impact of different energy efficiency solutions. They started off first as 30% guides, and they were very specific to a number of different uses. You can think of them as kind of a cookbook or as a instruction book on how to actually achieve this kind of goal. So they started with 30% guidance. About 10 years ago, a little more than that, we moved to 50% guidance and produced guides in the areas listed there. And then more recently, we've switched to zero energy guides and already published and on the street are K-12 schools, as well as small to medium offices. In this presentation, I want to focus a little bit on the multifamily guide, which is expected late this year, probably going to be early next year at this point. These guides are distributed primarily electronically through ASHRAE's website as the publisher. And you can see that we are just shy of 700,000 of these out there, both in print copy as well as electronic copy. But really it's leveraging these top professional organizations which provide a constant validation process, provide industry experts, meshing that with analysis from the national labs, and then supporting it with actual case studies. It is put together primarily by volunteer experts that form a project committee for each guide, representing the different disciplines needed to actually achieve zero energy in the design phase of a project. Next slide. So these guides, and again, I'm going to focus my comments specifically on multifamily, but there's similarities between all of these zero energy guides. That guidance is provided by these building types as well as by climate zone. And so the solutions change depending on where you are. And I already mentioned the variability in solar gain, but the systems that go in the building and really the consumption part becomes critically important to get that number down such that the renewable energy can meet the load. And then we have case studies in the guide that support the energy uses and the strategies that we've used. And really it's substantially beyond code. We haven't done the energy, kind of the comparison analysis yet on the multifamily guide, but for example, on the K-12 school guide, the recommendations in the guide are about 40% better than the latest version of ASHRAE 90.1. Next slide. So looking at kind of, we'll open the cover here a little bit and see what's in it. The first part really talks about the definitions and the processes. It provides, later in the book, a solution set by climate zone. They are a mix of prescriptive, that is, use this efficiency, use this amount of insulation, but there's also a lot of performance-based approaches. So such as try to meet this lighting power density, try to achieve these plug loads, look at the overall energy performance of the building and hit a specific energy use target. And there's guidance on all of these very specific strategies. A lot of it has to do with whole building integration. So if you can get your envelope loads down to a certain point, that opens the door to a lot of very efficient HVAC systems that could not be considered in a typical building. We also provide considerations when using new technologies in the field. One that sticks out on this particular guide is really looking at producing domestic hot water, because that's a major user in the multifamily buildings. There are recommended energy targets, so owners can look at those energy targets and use them as guides for design teams and contractors for something to achieve. Design teams can use those as goals in order to try to kind of self-push themselves to getting the level of energy efficiency that we know is achievable. And then we have examples of buildings, and the examples are critically important here. To show that they have performance data and that these buildings really work, but also real buildings are built with real dollars. And to show people that these dollars and the business case can be put together in a way that makes sense and that works for investors or tenants or owners, whoever is actually kind of in charge of that business case piece of it. Next slide. Primarily, the audience is kind of the architects and the engineering community, those that are really making the design decisions. We find another use case, though, in the building owners, where they can gain confidence and look at what their risk is in trying to deliver a building like this and say, yes, these EUIs are achievable, others are doing it, and use it as a mechanism to hand off to design teams in order to get this level of performance. Next. Very quickly, the guide is broken down into an introduction, rationale for why these things are important, the keys to success, how do you put teams together, how do you make decisions. There is a chapter on building simulation and modeling, creating a building such that you know how it's going to perform before it actually has to really perform. And then the bulk of the book is our how-to strategies. And there are roughly 200 how-to strategies in each of these guides, broken down by different disciplines. Next slide. And just as an example of some of those different disciplines, it's building and site planning, envelope, daylighting, electric lighting. We do hit plug load management, which is really important for multifamily, something that design teams don't normally think about, but how do you strategize to actually reduce the plug loads when you might not have total control over that because you don't know what tenants are going to bring in, but strategies to work with that. Service water heating or domestic hot water, heating and cooling systems, and then there is a little bit of renewable energy. This is not a renewable energy guide. It really is focused on how to get the loads down in the building and hit the EUI target. Next slide. We did provide modeling support for these and model actual kind of floor plates of buildings that would mimic multifamily, and it's been a little bit kind of made a generic model. The first floor in these buildings is commercial space, and it could be kind of a light plug load retail operation. This one had a little coffee shop in it. It could be kind of community space and office space. To represent kind of what goes on in the first floor of a lot of these buildings, and then tenant spaces up above, residential tenant above. Next. Those EUI targets that we calculate do change by climate zone, and so you can see the different climate zones here. This is actually represents the worldwide set of climate zones by adding climate zone 0 into the mix. These are the ASHRAE climate zones. And you can see how they do change with different climate. But as you look at this, there's definitely a lot of heat that goes into, or a lot of energy that goes into the internal equipment. Those are those plug loads. There is some lighting, although in this sector it's not as large. And then domestic hot water heating is a significant portion of it. This actually already incorporates heat pump hot water heaters, which is why it might not be as big as you might expect just looking at a generic chart of energy use of multifamily buildings, because we did take a lot of actions in order to reduce the domestic hot water load. Next slide. The density, interesting in doing this, that the density does matter in terms of how many 1-bedroom, 2-bedroom, and 3-bedroom apartments you have, because in a 1-bedroom scenario, you're going to end up with a lot more refrigeration in that. And so we did look at how those different densities change in the buildings with the different climate zones. Next slide. This is just an example of a water source heat pump and the type of guidance that's given and some of the specifications, recommendations that are provided, in this case for different COPs and efficiency of equipment. Next. And then finally, we do have some case studies. I have just one slide here as an example. This one's in Seattle, Washington. It is definitely a little bit of a chicken and egg because you're trying to find case studies that have very good EUIs. This EUI was 16.5, which is lower than what we're recommending. And then looking at those different strategies to get to that EUI, but showing that that is very consistent with what our model is predicting, as well as what the technical experts that form the committee have put together. So there's really kind of 3 aspects of this all rolled together. Next slide. They are free and available through that website. They are available from ASHRAE at that website. And again, we are expecting this to be out now early next year. I also want to mention that AIA, USGBC, and ASHRAE now have online training on the Advanced Energy Design Guides, and you can go to their continuing ed websites and actually take an 8-hour training class on the design guides. Next. And just very quickly, here's an example of some thermal bridging, lots of examples of just how to do this. And so we kind of have the what in trying to achieve low energy. These guys really focus on the how. How do you actually make it happen? How do you make those design decisions in order to get the energy performance that we all want? Next. And again, same on the envelope and looking at continuous air barrier, starting to talk about pressure testing buildings to make sure that the envelope is of very high quality. Next. And I will wrap up there. I would encourage you, if you have questions, to enter them as Connie had talked about at the beginning, and we'll address those later.
Terrific. Thank you, Paul. It sounds like a wonderful guide. I'm eager to get my hands on it. And you had mentioned that will be published in early January. Is that correct?
That is currently the plan. We're always working with, the schedules this year, as many know, have been challenged on many fronts. And so we are going to get it out as soon as we can. It is done and drafted and in the publishing process now. Fantastic.
Well, it sounds like you really got something in there for everybody, practitioners, designers, architects, engineers, but it's also, from where I sit as a lender, the examples with performance data that these techniques really work is so key. We as a lender, we're interested in comps. And so the more comps that we can point to, the more aggressive we can be in our underwriting. So that's terrific. So next, we will hear from Maya Gantley, project manager at the Association for Energy Affordability, and she'll take us through a case study from California. Maya, the mic is yours.
Hi, everyone. So my name is Maya Gantley, and I'm with the Association for Energy Affordability, AEA, which is a nonprofit that implements and provides technical assistance to an array of multifamily affordable housing energy efficiency programs in New York and California. And today I'll be talking about a California case study that went through one of these energy efficiency programs and completed a deep retrofit and approached net zero. All right. So for every project, we try to utilize these three principles, especially kind of, so the first one is reducing your overall energy demand. So this is really focusing on air sealing and insulation and really improving the overall building envelope. Secondly, we look at using all electric systems. And what we're really talking about here is heat pump based systems. So heat pump water heaters and heat pump HVAC rather than electric resistance, lower efficiency electric systems. And then third, we offset with on-site renewables. And really ideally, we're talking about PV systems. So the three main design challenges we face on nearly every project would be electrical capacity, cost, and knowledge and comfort. And so first off, for electrical capacity, honestly, this really can be a challenge, and it sometimes does stop a project in its tracks from moving forward with electrification. But often it is possible for many projects, and it's really key to investigate and look closely at your load assumptions and your load, and even maybe complete load monitoring to really dial in your HVAC sizing. Especially for retrofits, offsetting even one or two key systems is still a really great achievement, even if you're not able to do all of them. And then for cost and knowledge, I would say these really go hand in hand, especially as we engage with owners and contractors, get them involved and educated about these technologies. We found that upfront or first costs can come down, and maintenance costs and kind of concerns around maintenance are often also alleviated. All right, so diving into our case study, today we're talking about a project in Wasco, California. It's located in the Central Valley, built in 1996, 36 units, and 44,000 square feet. And this was a 9% TCAC project as well. So there was a larger scope beyond the energy efficiency that we were looking at. So the first kind of chunk of the scope is some of the the low-hanging fruit, so including LEDs, low flows, and high efficiency refrigerators. And then we focused in on improving the envelope through attic air sealing and insulation, as well as double pane windows, and also improving the ductwork. Then we fuel switched from in-unit gas water heaters to in-unit heat pump water heaters, and in-unit gas furnaces and ACs to high-efficiency inverter-driven heat pumps. And lastly, we offset with on-site renewables, a 110 kW solar array, 93% of which was allocated to resident bills. And then just really quickly about the project cost. So the total cost of the retrofit of this scope was $1 million. And then the various leverage funds that we were able to utilize were around $540,000. And so therefore the out-of-pocket cost for the owner was $460,000. So this is probably a little bit higher cost than standard, and part of this is because TCAC costs are often inclusive of other trades. So I will say that this exact same owner has done very similar scope projects at much lower install costs, with maybe resulting in 100 or 150K out of pocket. So the first main envelope improvement was the pretty standard attic insulation along with air sealing below. And then we also have aero-sealed duct sealing. So this is a kind of maybe a more advanced technology than standard, but for those that aren't familiar, you essentially pressurize your ductwork, spray this foam that goes into covers every small hole, and can bring duct leakage from say 25% down to 5%. So it's super effective, but it does come at a cost premium. So a cheaper alternative could definitely be done with hand sealing, boots to drywall, even cleaning and lining your return plenum. There's a lot that you can do for a much cheaper cost that will have still a really great impact. So for HVAC electrification, you can see for this project we had exterior closets for mechanical and plumbing. So on the left we have our furnace and AC combo, and on the right we have our new air handler and our inverter-driven heat pump. So with this inverter-driven heat pump, it has a variable speed compressor. So it's super high efficiency, super quiet, and it doesn't require any electric resistance heating backup because it operates well at low temperatures. Again, this one does also come at a cost premium. However, it's definitely worth considering in cold climates. So I think it's well worth your time to evaluate all options on the table. So for our water heating, this was also in unit, and we replaced the standard gas water heater on the left with a new heat pump water heater. So as a reminder, heat pumps move heat from one place to another. So in this case, the water heater is moving heat from the air outside into the water, very basically. And what you're left with is cool air. So either this can often be just left, distributed into the closet that it's located in, but sometimes you may need to duct that to the exterior to improve the capacity, to improve the efficiency of the heat pump. And that was the case in this project where we did need to duct that cold air to the exterior. And then lastly, we'd had solar PV on this project. So we were able to utilize virtual net energy metering, which was really key. So for folks outside of California, it essentially allows us to use a commercial size system, but allocates a percentage of the production to each unit. And especially for affordable multifamily properties and with all in-unit systems, this was really key to making the project a success. All right, so diving into the data, which I know most folks are really interested about. So right here, we're looking at total residential energy use in kBTU monthly pre and post construction. So we have natural gas in orange, electricity in blue, and then our PV solar is in yellow and is not factored into the electricity post occupancy. So you'll notice that we still do have a small amount of gas remaining, and this was because we were not able to offset the cooking at the property. And this was ultimately limited by the electrical capacity, and we weren't able to do any panel upgrades, so that was a limitation. Overall, we saw really high energy savings of 44%, and we're not looking at really a passive house retrofit. Like, these are really basic energy efficiency scope measures, but we're seeing really high savings. So the realized annual energy savings was 44%, 77% gas savings, and a slight increase in the electricity usage. So most folks ask, okay, great, you saved a bunch of energy, but what happened to the residential meters and their utility bills? So we're looking at, again, total residential meter energy cost per month before and after, and again, PV is separate from this. So what we saw is ultimately from energy efficiency only, we still saw cost savings of 18% or just over $8,000 per year. And then including solar, we saw 68%, which is equivalent to $30,400 per year. This translates to about $830 per year per resident, which is really impactful for these low-income communities. And I will say this was our projected number, and upon further analysis, we ended up seeing 70% cost savings overall. So some lessons learned and takeaways. So as I mentioned, we were not able to offset our cooking, our gas end use. That's our final end use at the property. And really, I think this came down to when we did this project. So we were evaluating the scope in 2017. Since then, we've learned a lot more about load monitoring and also sizing the HVAC system. So I think perhaps if we were doing the project today, there's a chance that we could have done additional unit heating and cooling load analysis, reduce the HVAC size, and perhaps even been able to offset the cooking. And then I'd just say that the retrofits, I think the key, really the best thing in our, like, everything else can go wrong, but if you don't have engaged owners and contractors, that is really where we see the most challenges without engaged owners and contractors. So I think that is ultimately our key to success, and really owners and contractors that are willing to take the time to find the right solutions for the specific property. And the main takeaway I want to leave you all with is that electrification is viable now for both new and existing buildings. And there are so many resources out there to make a project successful, especially one like Paul just reviewed. And lastly, I did want to mention that I know we only talked about in-unit systems today, but we are seeing a lot of success with central electrification and central heat pump water heating systems. There definitely are some key design considerations that are very important, so feel free to drop those questions in the Q&A, and maybe we can get to those later. Thanks so much.
Great, thank you, Maya. Lastly, we will hear from Waleed. He's going to present on a new construction, high-performance, affordable multifamily project in New Orleans.
All right, can you hear me?
Yes, loud and clear.
All right. So just a disclaimer, this is a presentation of work I've done as the sustainability enabler at SQ Dumas Ripple, an architectural firm in New Orleans, Louisiana. All right, we skipped a slide. That was just to set up the mood, but that was a picture of the New Orleans marshes. So the building that I'm going to be talking about is an affordable multifamily housing, about 45,000 square feet, 3 floors high, and about 50 apartments, and it's a 1- and 2-bedroom apartments. It's located in New Orleans. The climate zone there is 2A, so it's hot and humid. And they have a lot of hurricanes. So that's something to look forward to and design for. The building was getting some light tech funding, so it had to be certified under Enterprise Green Communities, which also required Energy Star. So although the building was certified under Energy Star for low-rise multifamily, what I'm going to be presenting today is based on the high-rise multifamily modeling protocol. And that's just because I have experience in it, and it also incorporates a lot of the common areas that we have in this building. So getting some lag. Oh, that's the courtyard. Just a picture. If you notice, the building is very modest in its appearance and very low window-to-wall ratio. So just for those who don't know New Orleans, the grid of the city, at least in this area, is at a 45-degree angle. So we don't have a lot of flexibility when it comes to the massing. But for orientation, we had some options, and we opted to have the building pointing southward, so to speak, and that would provide most shading for the courtyard, and it also maximizes the area for solar access for the solar panels. And overall, the roof area is about 15,000 square feet. So when we started out this, there were 2 questions, and we had 2 parallel exercises, and there's a supply and demand issue. So the first question is, what is the lowest EUI possible for a residential building that is possible in this climate zone? And the second question is, with the form and massing that we have, what's the highest energy output we can get on this roof, which is a 15,000 square feet, as I mentioned. So based on some research that we found, an EUI of 15 kBTU per square foot per year was possible, though when we did our modeling, we realized that it's closer to 17, and I think 15 was more of a single family residential, which is a little bit larger, but with multifamily, high density multifamily, it was close to 17. For reference, the Energy Star EUI was about 32, and the regional average based on the target finder was about 48. So we're cutting that by about 2/3. On the other hand, what's the highest energy output possible on this roof? We realized, or we figured out that it's about 19, and that's using premium panels and having reasonably good coverage of the building. It's about 80%, 75 to 80% coverage. New Orleans didn't have a lot of rules when it comes to clearance, so we ended up having solar panels up to about, I think, 18 inches from the edge of the roof, and there are no parapets for the architects out there. So that's about 255,000 kilowatt hours annually. So the goal here is to design the cheapest building we can that is below that 19 EUI, and we know that we can get a building as low as 17. And so we have this 2, kBTU per square foot per year buffer that we can work in. Picture the solar panels on the breezeway. And that's downtown New Orleans in the background.
Are you having some trouble with advancing?
Yeah, I think, Connie, if you can take it from here.
Sure.
All right, so we used eQuest, the famous simulation software to model this. We followed, like I said, the multifamily high-rise protocol, and it was straightforward. Next. So our instinct was to start out by modeling advanced HVAC systems. And what you see on the far left here was the baseline. I think it's a C or 13, I forgot. But it's about, the EUI just about 25. And then we modeled a few other ones. So we increased the heat pump or the air conditioner C rating to 15 and then 17. Those were available in the market. And then we also had a VRF system with local exhaust, and then VRF with DOS and ERVs on them. And we didn't model a geothermal just because we thought, based on market research, that it was just not possible with the soil type that we had in New Orleans. But as you can see here, the savings are pretty modest, and the premium for each of these systems gets increases quite a bit significantly. So we're looking from the baseline to the VRF and DOS with ERV, we're looking at about 300,000 plus premium. And the savings on it is like 2 units of EUI, and we know that we need to hit at least 19. So that wasn't the answer. Next, Connie. That wasn't the answer, looking at the HVAC system. And so we looked at the next slide. Yes, thank you. We looked at all the systems of the building, and we realized that all of them actually matter. And so when you look at this chart, you realize that envelope, at first, we didn't think that it was a big deal. But there was one trick that we had to that we utilized that made the savings exceed 30% from the baseline or from the energy code baseline. Lighting is not as a big deal in this building type, in our experience. But again, HVAC, domestic hot water, and appliances, they all contribute to the absolute EUI that we got. And as you see, we've managed to hit an 18 EUI of 18 kBTU per square foot per year. Next. This is broken down a little bit further by measure. And what you see there's a big drop in the envelope measure, where we model the infiltration rate from a very loose, I think it's 5 air changes per hour, to I think it was like 0.5 air changes per hour. And that comes from the building code, and 0.4 CFM per square foot of envelope area comes from a more advanced energy code. I think it's the 2013 version. Background, ASHRAE 19.1 2007 is the energy standard of the state of Louisiana. I forgot to mention that. So we were, our baseline is pretty low. And it doesn't sort of help us a lot when we present these cases to clients to have a model or a model code, model standard that low. Next. Picture of the solar panels on the roof, battery system. Next. So this here shows you an idea of the makeup of the appliances in the building, or in a multifamily building. And at a glance, what you see here is that the refrigerator is about 35%, and the clothes dryer is about 35%. And then the washers and the dishwashers are about 11 and 19%. I don't include the microwave or the oven here because it's electric resistant, so we don't have a lot of leeway there. But what this chart tells you is focus on the clothes dryers and refrigerators when you spec out these things, and make sure that you choose the most efficient ones there, because they have the biggest contribution to your appliance profile. Next. In this slide, it's a continuation of the slide before, and we look at what the baseline for each appliance type is, what the Energy Star entry level is, and what we had spec'd in this building. And the ones we spec'd were from the Energy Star list. And you can see, for example, in the clothes dryers, it's almost 75% more efficient than the baseline. And that's a big deal. And that actually got us to where we needed to be at an EOI of 18. Next. This picture, this chart here is pretty important for those who are concerned more about the cost of measures on return on investment. What you see here is savings in kilowatt hours for each $10,000 of initial cost. And what you notice is that with premium appliances and heat pump water heaters, you get far more bang for your buck than you do by installing a VRF with DOS and ERV on it, on your building. So it's important to know where to put your money, and we actually ended up installing a more inferior, or like a Sears 15 heat pump system, and we took the money that was allocated for the HVAC and we put it in the heat pumps and the appliances. Next. So the secret sauce, so to speak, is first air tightness, and that made us hit our target by a large degree. Next, second was heat pump water heaters. Next, and the third one is the ultra efficient appliances. Next. The regional average cost for construction of this building type in New Orleans was about $225 per square foot. It's a low-rise stick frame multifamily residential building. Next. And we built this building all in with a battery system and a solar system for about $164 per square foot. As you can see, the building had absolutely no finishes to trade off. It was, bare bones, and we still managed to get it 27% below market average, and net zero and resilient because it has a battery system that kicks in when the hurricane hits and the grid goes down. Next. Next. Some explorations early in the project. Next. We haven't had an update on the measured data in a few months, but the building was occupied in January, and it started increasing energy consumption, and there's a profile that is closely tracks what is modeled, which is the dark line at the top. The line at the bottom is actual energy, and around May is when they actually hit almost 90% occupancy, and we look forward to having this information and hopefully sharing it with everybody. But as of yet, we don't have that update. Next. And that's it. That's the last slide. Overall picture of the building. And thank you.
Thank you, Walid. That was terrific. I'd like to invite everyone in to join me in a virtual round of applause for our panelists. That was terrific. Thank you, everyone, very much. We learned about the technical guidance and resources available from NREL, and Paul walked us through the new Advanced Energy Design Guide for achieving zero energy. And then Maya and Walid, thank you for taking us through the design and practice for both new construction and retrofit projects. It was really interesting to see that. I found it particularly remarkable just to see the significant energy and cost savings. And just while the audience is kind of thinking of some of their questions, I'll just pose a few questions to the panelists. I guess this one is kind of specifically to Maya and Walid. In addition to the cost savings, I'm just curious if the tenants have reported back on some of their kind of perspective of living in a high performance building, of maintaining temperatures or reduced noise and odors from other apartments due to kind of those improved insulation and air sealing. Just kind of curious if you've received some feedback from tenants, and if so, what that is.
Sure. I can't maybe speak to the project I spoke on today specifically, but in general, I think we've noticed, especially with improved insulation, and I'll say in California, we can get away with not too much insulation, so really improved wall
Maya.
provides a lot more. Oh,
Maya, you're cutting out a bit.
oops, can you hear me now?
We're hearing about half the words you're saying, I think.
Okay.
Sorry about that.
If I may, I don't have a lot of feedback from the tenants yet, but when Hurricane Zeta hit a few months ago, the building was one of the only buildings in town that maintained power because the battery system was fully charged and went into effect, and we had a citywide blackout, actually region-wide probably blackout. So I'm pretty sure they were thrilled to have power when everybody else didn't.
I imagine, yes. Which actually kind of leads me to another question I have, which is really for all the panelists. I'm just curious if you can talk a little bit about the non-energy benefits as a result of designing and building to high performance standards, net zero energy. Walid, I think you're kind of referencing resiliency and some of the benefits there, obviously being located in New Orleans. There's the greenhouse gas emissions reductions and health benefits. I'm just curious if if you're tracking these things, or if there's some kind of additional benefits that maybe weren't called out here, but that you'd like to kind of highlight the audience.
We never heard complaints of gas leaks because we don't have any gas on site. I guess that's the benefit of electrification.
Well, so many of the you know, the issues come when you try to quantify those benefits and use them as part of the business case. And I actually think that can be a struggle, but a lot of these other soft benefits you start to mention, people really do appreciate, and I think ultimately do get factored into the value of that building, right? So whether it's more weather resilient, whether you can have some operations with the power grid going down, whether or not the buildings are more comfortable because they're not drafty, especially compared to older buildings. We have in the design guides started putting little icons on things where there are other benefits other than just energy, right? And I would say that that's kind of energy and kind of the carbon impact of using that energy. But things like resiliency, things like, are there strategies you can put in that actually save you money with that? Are there strategies that you know, can make the building, I guess I already mentioned the resiliency piece of it, but you know, trying to get at, you know, all these other benefits, and there are lots of them.
Thanks, Paul. Yeah, no, I agree. It is a challenge to quantify those. We're aware of them, but right, how do we actually kind of work those into some of our pro formas and so on? You know, I think we're getting there, but
Yeah.
I agree we still have some ways to go. So thanks again to the panelists. Connie, I'll pass it over to you. If we've got some Q&A from the audience, I would want to save a bit of time for that. So.
Okay, well, we are running short. Let's
Yes.
look here. So one of the questions, there was only one cold climate site. What is the degree day value for heating in Seattle for comparison for the Northerners on the line today? Pretty technical.
Say that again.
I'm sorry. There was only one cold climate site mentioned today in the case studies or in the conversation. What is the degree day value for heating in Seattle as a comparison for the Northerners on the line?
I would have to look that up. I don't know it off the top of my head. Sorry.
I was trying to get a quick fact-based one out before we closed up today. So we can have some follow-up later. But it is 10:58 Portland, Oregon time where I'm sitting. And I want to thank everybody for joining us today. I have a couple quick little plugs. The Getting to Zero resource hub is available to help you on your path to zero. You can go to the link there and find 300 zero energy and carbon resources across these topic areas. Lots of resources available for you there. And for those of you who are frequent flyers on our webinars, maybe you missed a session along the way, you can find our whole archive there on our website. And be the first to hear about these events. You can follow us on Twitter and LinkedIn, and you will hear about these pretty quick. And as a reminder, you will receive an email tomorrow with links to the on-demand recording, a PDF of the slides, and a certificate of attendance for your participation today. So thank you again for joining us. Thanks to our presenters. Thanks to Atalia for moderating today. That was fantastic. Make sure to fill out that survey if you are seeking AIA credits. And please stay safe and stay well. Thank you.